How do you balance PID overshoot and response time? Imagine trying to make a hot cup of coffee just right. You want it to cool down quickly but not spill over. That's what balancing overshoot and response time in a PID controller feels like. When you tune a PID, you adjust three parts: proportional, integral, and derivative gains. Each one influences how fast and how smoothly the system responds. If you set the proportional gain too high, the system reacts quickly, but it can overshoot the target and start oscillating. Lowering it makes the response slower but reduces overshoot. The integral gain helps eliminate steady-state errors, but if it's too high, it can cause the system to overshoot or become unstable. The derivative gain predicts future errors based on the current rate of change, helping to dampen oscillations and improve stability. To find a good balance, start with the proportional gain. Increase it until the system begins to oscillate, then cut it back to about half that value. Next, add a small amount of integral gain to eliminate any steady-state error, but watch out for increased overshoot. Once you have a stable response, introduce the derivative gain. This helps reduce overshoot and makes the system settle faster. Practicing this process step by step is key. Set the integral and derivative gains to 0 first. Then increase the proportional gain until you see oscillations. Cut it back to a stable level. Add a little integral gain to remove any offset, but do it gradually. Finally, add derivative gain to smooth out the response and cut down on overshoot. Other tricks include smoothing the input signal to prevent sudden changes that cause overshoot. Limiting the maximum output of the controller can also help avoid aggressive actions that lead to overshoot. Sometimes, turning off the integral part during large errors can prevent the system from reacting too strongly. In real-world applications like motor speed control or power electronics, these tuning methods are essential. They help you respond quickly without risking damage from overshoot or instability. Using software tools or simulation programs can make tuning easier by showing how different settings affect the system. In the end, balancing overshoot and response time is about adjusting the three gains to find a middle ground. Higher proportional gain speeds things up but can cause overshoot. Adding integral gain removes steady-state error but might worsen overshoot if not tuned carefully. Derivative gain helps stabilize the system and reduce overshoot. Combining these methods with setpoint filtering and output limits can give you a well-behaved, responsive control system.